Hello class, this is Ms. Riggins with today's video on section 5.2 Logarithms and Exponential Models. As you're watching the video, please remember to write down important notes, equations, formulas, or statements. Feel free to pause, rewind, or even replay the video as often as you need. And at the end of watching the video, write down your summary in your notes and then submit the summary as well as a top question via the online whisk before class. All right, let's begin. Today's section is going to be about topics that we've already covered, but how we're going to use them together to solve real-world problems. Model is an example, is basically a function that is used to describe a real-world situation. And exponential models are exponential functions that are used to describe real-world situations. And we've looked at it in terms of financially with compound interest and things of that sort. But today we're going to look at it in a different light, and that's in the terms of growth and decay for population as well as lack of population. All right, let's begin. So if you ever see a population growth, most of the time, 90% of the time, it's described using an exponential growth function that looks something like this, where n represents the population size at time t, n naught represents the initial population at the initial time, and r represents the relative growth rate. Now this is a little bit different because a lot of you maybe see a growth rate and want to put in, for the base, instead of e, you might want to put in 1 plus the growth rate as the base, and that is sometimes okay, but in this case, if you ever see the word relative growth rate, then it's going to look like this situation where you have the base of the exponential function is the constant e. And some of you may be looking at this and says, this looks very familiar. And the reason it looks very familiar for you is because you've seen this expression before, and that's in the terms of continuously compounded interest. And the reason why these are the exact same equations is if we take a look, if you remember, for continuously compounding interest, interest is being applied or growth is being occurred every second or every millisecond at every moment of time, not just once a year, twice a year, 12 times a year, 365 times a year. Whereas in continuously compounded, it's applied every moment. Well, think about population. Babies aren't just born once a year, once a month, once a day. Babies are being born in population all the time, sometimes more than once. But anyway, and so that's why the relative growth rate can be used in an exponential sense with the natural base than with just a particular 1 plus base. So whenever you see relative rate of growth, know that you're going to use this model where this model has e as the base, not 1 plus r as the base. Okay? So let's take a look at an example and see how we would apply it. The population of the world in 2000 was 6.1 billion. The estimated relative growth rate, there is that relative growth rate, was 1.4% per year. If the population continues to grow at this rate, when will it reach 122 billion? Well, the first thing we have to do is we have to write the exponential model. And because they use relative growth rate, our model is going to look something like this, where 6.1 was the initial population at time t equals 0, our year 2000, and then r is 0.014, the decimal value for 1.4%, and our base is e. So we're not going to actually use 1 plus 0.014 as our base. We're using our base as e. And if we want to figure out when will the population reach 122 billion, well, in the past, we would have to go to our graphing calculator, graph the original function plus the horizontal line where 122, and then we would have to use the calculator to find the intersection either by tracing or using the intersection tool, and we would get our answer. Well, what if we don't have a graphing calculator? How will you answer this problem? Well, that's where we apply the logarithms. And so in this case, before we can apply the logarithm, we have to get the exponential part by itself on one side of the equation. So we have to get rid of the 6.1 from both sides. So we divide both sides by 6.1. And then we take the natural log of both sides. And the only reason we're taking the natural log is because our base is e. If not, we just take the log with the same base. And then once you do that, on the right hand side, the natural log gets rid of the e, and we're just left with 0.014t. And when we do our math, this is what we're going to put into the calculator. Natural log of 122 divided by 6.1. And then divide that answer by 0.014, and the answer you get will be around 213.981 years, which rounds up to 214 for total years. So two ways you can solve this problem, but this way is using algebra. The other way was using the graphing calculator. Okay, second concept we want to talk about today is the concept of doubling time and half time. So in exponential growth, a doubling time is basically the time required for a value to double. And so how do you determine how long it will take for a value to double in that model that you have? So say, for example, this is our very general model where n represents the number that we want and n naught represents the initial number. Well, since we want double of, let's say, the original value, then that means n can represent 2 times n naught. So we go from here to here. Oops, sorry. Okay, and then we apply our algebra to solve this problem. Get the exponential part by itself by dividing by n. So we get 2 is equal to e to the rt. And ln of 2 is equal to rt. Divide both sides by r. And there we have the time it would take to double. So if we use our example from the previous problem where our r was 0.014, we go to our calculator and we, let's add another calculator page, Control I, sorry, thought I did this already. Calculator 1, and we do natural log, and you have to put in parentheses, divided by our relative growth rate, which was 0.014. And our answer is around 49.5. So it means that it's going to take approximately 50 years for the amount to double, the initial amount to double. Now let's see if that works in our problem. If we go to menu, well, let me get rid of the y equals 122. We don't need that anymore. If we want to figure out what happens in 49.5 years, we can do menu. I'm showing you another feature of the calculator, trace, and graph trace. And the reason why I like graph trace is I can put an actual value in. I'm going to type in 49.5 because that's what it said it took to double. And it will take me to that point, and then it will show me, sorry, move this up so you can see it. It will show me the value of 12.2, 49.5 and 12.2, which makes sense because our initial value was 6.1. And now our new value is 12.2, which it has doubled. Two things I want to point out. Now we could also solve this by basically going up here and adding another page, another function of 12.2, and then doing menu, analyze, intersection, and finding the intersection as well. It would have given us the same answer, but now we have two ways of finding this on the graphing calculator. All right, but I want to point out that we can only use this formula of natural log of 2 over r when our base is e. Okay, if our base is not e, then the formula that we're going to use for the doubling time, to make it really big, is log of whatever base that we're dealing with. Let me put that in. I'm going to say b, and then we would say 2 as well, and we'd be ready to go. Divided by r. Oops, sorry. Okay, to figure out the doubling time. All right, any questions? Well, I won't be able to hear them, so let's move on. Now, if I want to find, what if I don't have an exponential growth? Oh, before I go, there is a rule of 70 that's not in your book, but another way of business people use to be able to figure out how much time it would take for your money to double is they take 70 and divide it by the percentage growth rate. So going back to our calculator, if we go back to our calculator page, and let's take 70 and divide it by, they say the percentage growth rate, so we're going to divide it by 1.4%, but we're not going to put percent, and we get around 50. And why is that the case? Well, if you take the natural log of 2 and the natural log of 2 is around 0.7, which is close to 70%. So this is like basically saying 70% divided by 1.4% will give you an answer close to your actual answer, not the exact one. So getting back to how do we find this for exponential decay? Well, we don't want the value to double. We want the value to decrease for exponential decay. And so the time required for the halving of the value, so taking in a value and dividing it by 2, the formula is very similar to the formula that we talked about. Oops, that's not it. Sorry. So if we had an exponential decay problem, the formula would look like this. Natural log of 1/2 divided by r will give you the halving time, and sometimes they'll call that h instead of t to note that it's the halving time, not the doubling time. And again, if we're not using a natural base, then we would have to use, instead of natural log of 1/2, we would have to use whatever base that we're using, the log of that 1/2 divided by r. Okay. Now, a little bit later in class, we're going to take a look at formulas to take advantage. What if we already know the doubling time and the halving time, but we don't know the growth rate? There are a couple formulas that you will need to know that we can use to predict future values. And so this is the formula for if we know the doubling value, and that would be D, but we don't know the growth rate. We can still figure out after so many years what value the next value will be using this formula. And I'll explain why a little bit later in class. And then for halving, we're still going to use this formula. If I already know the half-life, h, then I can predict what a future value will be for some time t without actually having the growth rate. Okay, so there are ways to solve exponential problems without knowing what the growth rate is. And these formulas prove that as well, or are examples of that. Okay, last thing we want to talk about is converting between q is equal to a times b to the t and q is equal to ae to the kt. So remember, we talked about for every exponential function, for b, we can always find a value k for which we can use this relationship. Okay. So for our example, if you remember, for our example, we used the relative growth rate of 0.014. So if I want to write that expression, instead of doing 6.1 times e to the 0.014 t, if I wanted to write that with a different base, I don't know why you would, but if you did, you could. And that is basically by doing 6.1 and trying to find out what e to the 0.014 is. Once you find out what z.014 is, then you'll be able to write that as my base. And so I go over here to my calculator and write what is e, and I have to use the e for there. Or I could use this function up here too. I don't know why I didn't. All right, I'm just making it hard on me. 0.014. Oops. And I get 1.0141, which is okay because when I go over here and graph it, if I want to graph this function, y is equal to 6.1 times 1.141 raised to the x power. What happened? Oh, 1.0141. I get the exact same expression. Okay. All right, that's it. This video is a little bit long because I was trying not to stop and break, but I hope you enjoyed it. Let me finish this off just so we can have some completeness. And that's the end of the video. So I hope you enjoyed it. All right, bye-bye.